In this paper, we present a novel method, CuNeRF, cube-based neural radiance field for zero-shot medical image arbitrary-scale super-resolution. Our goal is to build a continuous volumetric representation from a single medical volume without any extra references. A well-trained CuNeRF can synthesize medical slices from free viewpoints. And can also supersample medical images with arbitrary scales in a continuous domain. Existing medical image super-resolution methods aim to fit the mappings between low-resolution and high-resolution medical volumes, which deeply rely on high-resolution images and can only deal with several upsampling scales, limiting their applications in various scenarios. To address these limitations, CuNeRF aims to build the coordinate intensity mapping instead of the above LR-hour mappings. As we can see, the blue and orange points are the low-resolution and high-resolution pixels, respectively. The goal of arbitrary-scale super-resolution is to build a continuous function based on those low-resolution points. Though CuNeRF can build continuous representations based on the discrete sampled views, its ray sampling strategy cannot cover the regions within the cubic regions, and thus cause spatial aliasing, yielding grid-like artifacts in its SR results. In contrast, CuNeRF employs cube-based sampling instead of ray sampling, which queries the points within the cube during optimization. Thus, the inner region of the cube can be covered by CuNeRF, achieving accurate and artifact-free results. Here is the overall framework of our CuNeRF. To render a pixel, CuNeRF first uniformly samples endpoints within the cube space. Then, CuNeRF obtains the coarse estimation by feeding the sampling points into an MLP to produce the corresponding pixel intensity and volume density. Subsequently, CuNeRF computes the coarse output of the target pixel via volume integral. We reform the volume rendering equation to adapt the cube instead of ray regions. Finally, CuNeRF resamples the points under the coarse estimation to acquire the fine estimation of the cube. The fine output is generated by the same procedures above. The fine output is the final result of the given pixel. We conduct comprehensive experiments and in-depth analysis to prove the correctness and effectiveness of the proposed methods. As we see, our CuNeRF outperforms state-of-the-art methods for 3D MISR on the MSD dataset. For volumetric MISR, our CuNeRF also achieves comparable performance to the state-of-the-art methods on the KITS-19 dataset. Note that CuNeRF is a zero-shot method. Thus the quantitative results prove the correctness of our motivations. The result of the ablation study demonstrates that the proposed cube-based sampling and isotropic volume rendering can significantly improve the reconstruction performance, proving the effectiveness of the proposed modules. The parametric analysis suggests our method is the parameter-insensitive method with good robustness under different experimental settings. Compared to state-of-the-art methods, our CuNeRF achieves better 3D and volumetric MISR results at various upsampling factors, yielding better visual verisimilitude and reducing objectionable artifacts. We also visualize the arbitrary scale and free viewpoint rendering results. As shown, CuNeRF can synthesize medical images at continuously valued scales. Moreover, CuNeRF can also yield medical slices with a viewpoint rotating 360 degrees around an arbitrary coordinate axis. In conclusion, CuNeRF can render medical images at desired views and scales, which is able to provide richer visual information than existing methods for clinical diagnosis. Thanks for watching. If you have any questions, please contact us.